Something that we found is that as we look out and we find one galaxy, there are usually other galaxies located nearby. These clusters of galaxies we cleverly name galaxy clusters. So we have these galaxy clusters. The galaxy cluster that the Milky Way is a part of is known as the local group of galaxies. This contains the Milky Way, the Andromeda, another spiral-type galaxy known as the Triangulum, and a whole bunch of dwarf satellite galaxies orbiting around all of them. Altogether, we found somewhere around 40 galaxies within the local group, with Milky Way, Andromeda, and Triangulum being the big ones. Now, when we look at where clusters of galaxies are located, we find that there are usually other galaxy clusters around. These clusters of galaxy clusters we call superclusters. Now, based off of observation, the difference between a cluster and a supercluster appears to be the amount of gravity. A galaxy cluster has enough galaxy that it's actually held together, meaning that those galaxies are orbiting around each other. Whereas a supercluster, the clusters are not held together. Okay, this is going to become more important later on when we talk more about the universe itself. Now, a typical supercluster contains dozens of clusters spread out over around 45 megaparsecs of space. This is around 150 million light years. Now, this diagram that we're looking at here has the local supercluster. So here at the center we have the Milky Way, and then each of these other dots are locations for other clusters. Now, of note, we have the Virgo and the Coma clusters. These two clusters are what are known as rich galaxy clusters. So we mentioned that within our Milky Way we had the three big ones, and then altogether somewhere around 40 if you include all of the dwarf satellite galaxies. In a rich galaxy cluster you can have thousands of galaxies in them. Okay, so they've got way more than what we see just in the local group. Now when we start to trace where superclusters are located in space, we start to form a network of galaxies that runs through the entire universe. So in this image, each dot is actually the position of a galaxy in our sky. And you can start to get this feel that we have these chains of galaxies running through. These are what are known as filaments. Okay, so these long chains of galaxies are filaments. And then in between, we get these pockets where we don't see anything. These are known as voids. Here is another view. The previous one was an all-sky view. This is actually a slice through space. So we have the Milky Way in the middle, and then what's happening as we get to greater distances. And again, you can see each of these black dots is actually the position of a galaxy, and we get the filaments and walls, and then in between we have these pockets where we don't find anything, known as voids. This is what we refer to as the large-scale structure. This is the scale of the universe on the largest sizes. So one way of kind of visualizing this in 3 dimensions is that the locations of the galaxies kind of are on the edges, and then in between you have the bubbles. So it's kind of like a foamy froth, okay, where the edges of the bubbles are where the galaxies are, and then in between you have the voids. Now, as we look at galaxy clusters, particularly rich galaxy clusters, these ones with thousands of galaxies in them, we find they're usually embedded at the center of an overall hot X-ray emitting cloud. We believe that this hot X-ray emitting cloud was actually produced due to galactic collision. The idea is that if you have two galaxies that are traveling really fast, as they collide into each other, it is going to cause a lot of friction through the interstellar medium, which is going to cause it to superheat and expand, forming into this X-ray emitting cloud. Now, not all collisions are going to be fast enough to produce these X-ray clouds. Instead, if we have a slower, gentler collision, then instead of leading to a lot of friction and heating of the interstellar medium, instead, it leads to a compression of the interstellar medium. And anytime you compress the interstellar medium, this is going to trigger star formation. So we actually see these galaxies that have huge amounts of star formation. These are what are known as starburst galaxies, because they have way more star formation than in a typical galaxy. A starburst galaxy will have around 100 times more star formation than a regular galaxy. Now, near misses and actual collisions will greatly change the overall appearance of the galaxies. So we have the tidal forces. Again, the tidal force is where the pull of gravity on one side of the object is greater than the pull of gravity on the other, and it leads to stretching forces. Okay? The tidal force can actually stretch a galaxy so much that some stars are actually ejected out of the galaxy into interstellar space. We can kind of see this happening here with the antenna galaxy. These two long streams are stars that are being ejected because of those tidal forces. Also in this one, you can see a lot of the blue. That is regions where we've had recent star formation. The antenna galaxy is one of these starburst galaxies having huge amounts of star formation. So when they first begin to collide, we have irregular type galaxies. However, eventually over time, we do expect them to settle down. When we have two galaxies of roughly the same side collide, both galaxies become highly changed. But eventually they settle down into a single much larger galaxy. This is what we call a galaxy merger. However, sometimes we have a large galaxy that will swallow up a smaller galaxy. When this happens, the big galaxy isn't really affected that much. It just gets a little bit bigger, but the small galaxy has now been swallowed up and becomes part of the much larger galaxy. This process of big galaxies eating up little galaxies is known as galactic cannibalism. We believe that the Milky Way is actually currently in the process of eating a galaxy, and we have some evidence that it has eaten at least 2 other galaxies previously.